Hello, can you hear me now? Okay, everybody there? All right. Okay, so I think we're ready to get started. Okay. Um, First, does anybody have a question about the homework assignment that's due this week? Is anybody a question that we could try to answer quickly? Is there anybody got any question they might want to ask? Okay. Yeah. If you do have, let's see. Oh, give it a try. Yeah, Ricky, you have a question? Go ahead and let's see what's the question. You can unmute yourself and just talk. Oh, okay. Okay. All right. So, okay, then let's just go ahead and yeah, I know. Let's go ahead and try let's go ahead and go back to base and bounds. So when we left off, uh we were doing the base and bounds mechanism for virtual address spaces. Okay. So, and we just started talking about the idea of multiple base and bounds. So what I'm doing is I'm going to download this zip file on virtual memory. I've downloaded it to this computer. Here's that folder. Okay. Here's the pictures that we were working with. Yeah. This is our picture for address translation. Virtual address goes into the memory management unit, something happens in the memory management unit, and a physical address comes out. And then we're going to be filling in what this inside here with three different implementations: base and bounds, segments, and page tables. Okay, so this is our idea that the CPU only knows virtual addresses. The physical memory, of course, only knows physical addresses. And then when the CPU is running a process, the memory management unit is configured for each process. So the address translation depends on which process is running. So each process sees its own piece of physical memory, but thinks it's its virtual memory. Okay, so like here's a picture with base and bounds. Okay, this had three processes, A, B, and C. This was process A, this was process B, this is process C, okay? And each process has a base and a bound register see, now the memory management unit shows a base and a bound register. Virtual addresses come in here, and if the remember, this is our translation formula down here. If a virtual address coming in here is less than the bound, so that means it doesn't go past the lower limit of this address space. If the virtual address is less than the bound, then you issue the base address plus the virtual address. You add the virtual address to the base. So the base points to the top of this space, and then the virtual address offsets you into the address space. So another word for the base, I'm sorry, another word for the virtual address is offset. It offsets you into the virtual address space. And when you switch from one process to another process, these registers have to go into the process control block of the process, and then these registers from another process have to be copied into the memory management unit. The memory management unit essentially becomes part of the CPU. It's all this is part of a process's state. It's CPU registers and its memory management unit. Okay, so that's the basics for base and bounds. This process can't this process can't read this process's memory, because for a base up here to access a memory down here would need an offset larger than the bound. So his base points up here. He can't go down here because the base would make the offset larger than the bound. And he can't go up here. It's not actually shown in here, but uh, the virtual addresses can never be negative numbers. So virtual addresses by definition are always positive numbers. So you can't somehow subtract your way down into these memory locations. So he can't subtract his way down to these memory locations because this is all positive numbers. Okay, so when you do base plus virtual address, you can only offset in the positive direction, but the bound keeps you from going past that limit, whatever the operating system set it for. So you can only go up to there. Okay. All right. So that's our basic idea. So that's a single pair of base and bounds. Now we could add multiple pairs of base and bounds. This is where we left off last week. We just started talking about the idea that you could have multiple base and bounds registers. Okay, now let me switch to, I'm going to draw on the picture. Okay. Okay, let's see. So here's our picture. Here's our picture with two base and bounds registers. Okay. Okay, here's we have two base and bound register, base 1, bound 1, base 2, bound 2. So we're trying to create now what we now call a process with two segments. So we're switching from base and bounds to we're switching to segments. So now we're going to create a process that has two segments. Okay, now that means the picture now would be for one process would be like over here. This is one process now. The one process has two pieces of virtual memory associated to it. Okay, so I'm sorry. The one process, I'm in the wrong tool. Oh, yeah, there. So this is one segment of this process's virtual address space, and this is another segment of this same process's virtual address space. All right, so the process has two segments of its virtual address space, okay? Base 1 points to, well, base 1 points to that base, and bound 1 gives the size of that segment of the virtual address space, and base 2 points to that base, and bound 2 creates that size of that virtual address space, okay? Let's try to figure out how a virtual address is translated. So here, here's a virtual address, okay? So the virtual address is n bits long, okay? So there's a virtual address with n bits. We're going to chop the virtual address into two pieces, okay? We're going to chop the virtual address into two pieces. One piece is going to be called the segment address. I'll just write it for S for segment. That's a lousy S. This part here is the segment. And then this part of the address over here is going to be called the offset. Okay, so the address is in two parts. And let's suppose that the segment is 3 bits. Okay, so there's like 3 bits of segment. Okay, ooh, that's really bad. Okay, so the n-bit virtual address has got 3 bits of segment, and then all the rest of the bits are offset. Okay, all right. Now, the main thing we have to do, now we're still going to be using the same idea for address translation. So the main idea for address translation was that the physical address equals, well, first you take the virtual address and you check that it's less than the bound. So you'd make that test. And then if that's correct, you take the virtual address and add it to the base. Okay. But if the test comes out false, you raise an interrupt. Okay. The interrupt is this line here, the error interrupt. So if somebody tries to access memory that's beyond their bound, then you halt the program. Now, what changes here? Here's what's going to change. Remember, we have two sets of, in this case, we have at least two base and bounds pairs. So down here, what we're going to do is we're going to think of the segment as an index into an array of bound registers. And we're going to think of the segment part of the address as an index into an array of base registers. So up here, we can imagine that there's two base registers and segment chooses which one of them. Okay, and there's two bound registers, and these 3 bits, they choose the bound register. Okay, now let me show you a picture that somebody else drew that kind of that shows this. If you go into this the zip file folder and you open this folder on using segments, here's a handout that somebody else created. It's kind of nice. It's got some good pictures in it. Okay. Here's another way to think about this picture that we're drawing here. Okay. Let's see. Okay. Let's see. I don't know if I can fit. Yeah. Okay. There. They're almost side by side. Okay. Here's let's see. Okay. Here's our CPU. In this picture, here's his CPU. Okay, the CPU issues an address. This is the address. The address is chopped up into 2 pieces, just like we showed here. The address is chopped into 2 pieces. He calls it S for the segment. I'm not sure why he uses the letter D for what would be the offset. Okay, now this bit, this part of the address goes up here and becomes an index into a table of base and bound registers. Now he calls bound limit. That seems to be a pretty common term for the bound. So he has the base register and the limit register. Okay, so this part of the address is an index into this array. The array is pairs of limit and base registers. The limit part goes down in here into the comparison. And you check if this comparison is true or false. If it's false, he should have shown this trap addressing error. He really just should have shown that error coming back up into the CPU, because that's what it does. It goes back to the CPU. It is the trap is another word for interrupt. There's so many words for all these different things. So a lot of people use the word trap because you're trapping the CPU into a certain segment, into a piece of code. The interrupt interrupts the CPU, but it traps the CPU into a segment of code, okay, into the interrupt handler. Okay, so it would be nice if he just showed that going up right back into the CPU as the trap. Okay, then if you pass this test, then the virtual address, the offset part of the virtual address goes into here, and the base part gets added to it. Okay, so actually over here in this picture here, I should have said that this is the offset part of the virtual address, and this is the offset part of the virtual address. So see, can I go back and change this? I don't think I can edit these. Let me see if I can edit that. No, you can't edit what you've typed in before. Yeah, you can't edit what you've typed in. It seems like I can't go back and unless there's a way I don't know how to do it. Okay. So when I wrote virtual address here, really should have said the offset part of the virtual address. Like this is the segment part of the virtual address. This is the offset part of the virtual address. So the offset part is compared to the bound. That you see that here. The virtual address is made up of 2 parts, the segment and the offset. The segment is an index into the base and bounds pairs. So this is an array of base and bound registers. Okay, and then the offset part goes in here, gets compared to the bound. If it passes the test, the base part is added to the offset to get the virtual address, to get the physical address in physical memory. Okay. We'll see this picture again when we use page tables. When we get to the next form of memory management, we get to page tables, they'll look a lot like this. In fact, this segment table is going to change meaning just a little bit and become the page table. Okay, so there'll be a subtle shift in the way we think about things, but this segment table is going to more or less become what we call now a page table. Okay. Now, usually in this kind of a setup, the segment register is just 3 or 4 bits. Most programs would have 1, 2, 3, 4, 5, up to maybe 8 segments. It wasn't very common when they did this to have more than a few segments. So the segment part of the virtual address is usually anywhere from 1 bit, which would just be 2. See, if I have only a base and if I only have 2 pairs of base and bounds registers, I really only need 1 bit up here. This would usually be anywhere from 1 bit to 4 bits. 4 bits would give you 16 pairs of base and bounds registers, which is quite a few. I don't even know if anyone ever did it with that many. Okay. Now, this the way people think of this is now a process. In this case, he's showing a process here is 1, 2, 3, 4, 5 segments. So we think of the process as being made of 1, 2, 3, 4, 5 virtual address spaces that are put into physical memory in different places. Like in this case, he's thinking, here's the main program. Okay, the main program is segment 2. So there's segment 2 in physical memory. He called something called the symbol table. Okay, so there's a bunch of variables. They're their own segment. The stack for the process's stack is its own segment. So that's segment 3. Okay. Then some functions, like here's 2 functions. These functions are considered their own segment. That's kind of odd to have a function as a segment. We'll see what really would be is these might be 2 libraries of functions. What would be much more reasonable is you'd have the main program, variables, stack, and then 2 libraries, which would be their own segments. A library down here and maybe a library up here. Okay. Then here's the table. This is the base and bounds table. Okay. And see, segment 0 has its size is 1,000. It's based at the address 1,400. So there's 1 segment. Okay. So then that table is what goes into this picture. Oops, that table goes into this table right here. Okay, this table is what's sitting inside the memory management unit. And again, remember, it's real important. This table becomes essentially part of the CPU when you do a context switch. The data in this table gets stored in the process control block, just like the registers of the CPU. Okay, so this would be a typical way of thinking when you write programs, that you would think of your program as chopped up into segments. Okay. The segments are laid out in memory any way the compiler wants them. The compiler takes care of these segments for you, and the compiler kind of decides where to lay them out. Okay. Now, what are the advantages of this? Like, why would we want multiple segments? Okay, we're gonna learn 3. Let's see. Make a note here. We're going to really see 3 advantages for segments. Okay. Okay. The first advantage is it helps solve, well, I shouldn't say solve, but helps solve internal fragmentation. Okay. So it helps solve internal fragmentation. The other thing it helps us do is it helps us lets processes share physical memory. So we'll talk about that. That's a real important idea, that the original base, when you had a single pair of base and bounds registers, there was no way that you could let processes share physical memory. We'll talk about why that's important. Essentially, it becomes important for 2 reasons. It becomes important for sharing code, okay, what Windows nowadays call DLLs, okay, and it lets you communicate, what we call inter-process communication, which is abbreviated IPC these days, inter-process communication. So DLLs and IPC, okay? So in a sense, we're learning two acronyms. When we do with this base and bound, you can let processes share physical memory, which in modern terms is referred to as DLLs. And you can also have processes talk to each other, and that's called inter-process communication. Okay. Now there's a third thing that we can do that's kind of neat. We can let processes have more virtual memory than there is shared than physical memory. This sounds very strange. How can a process have more virtual memory? How can a process can appear to be larger than physical memory? Okay. Okay. And this is actually very, very important things. This is what lets programs work with massive data sets. This is how modern programs work with huge data sets, by doing a trick where you can have more virtual memory than there is physical memory. So, and we'll see that when we do page tables do 2 and 3, and page tables do all 3 of these even better than segments do. Okay, so we're going to introduce these ideas with segments. We'll see how segments help solve internal fragmentation, how they let us share physical memory, and how they let us have more virtual memory than physical memory. Page tables do all 3 of these even better, but it's nicer to page tables are really complicated. Introducing these ideas with page tables is just really complicated. So if we introduce these ideas with simpler segments, then it's not so hard to see how page tables do these things better. Okay, there is one big disadvantage. The main, well, I should say not one big, but the main disadvantage external fragmentation. Okay, this is what page tables are going to solve that segments don't solve. Okay, the main disadvantage is external fragmentation. Segments don't help us solve this. So what we want to do is kind of go through and talk about these ideas now. This is kind of in our outline of what we want to do. Okay, let me save this. Okay, so we want to see that there's going to be three advantages to segments, and then there's going to be this one big disadvantage. When we jump to page tables will do these even more elegantly, though not easily. It's hard to explain, but it does these 3 even more elegantly, and it also solves real well this notion of external fragmentation. Okay, all right. So, okay, let's talk about internal fragmentation. All right. Now, there's no picture of that in this file here. There's no picture in here that explains the internal fragmentation. So let's go to our textbook's got kind of a picture that gives you a sense of that. Here's internal fragmentation. Okay. Internal fragmentation is when you have in your process empty space that's just not being used. Okay. So when you have empty space in your process that isn't being used, we think of that as memory is fragmented. There's chunks of memory that aren't being used, and they're just unused. Okay. Now, the reason that this has this big chunk of empty space is so that the heap can grow down this way and the stack can grow up this way and they can meet. And you leave it a big empty space in between so that you don't know which one can grow more. There's a limit to how they can't both grow a lot, but you could have this one grow a medium amount and this one grow a medium amount. Some programs might have this one grow a little, but this one grow a lot. Some might have this one grow a little and have this one grow a lot. So, it's kind of a clever way to arrange it so that without knowing ahead of time which one wants to grow, you can have either one grow, but you can't have both of them grow a lot. Okay, but this is wasted space. What if neither one of them grows? What if it's a very small program and it really doesn't need much heap space and it doesn't need much stack space? Then all this allocated space here is just kind of wasted. That wasted space is internal fragmentation. Okay, so what you would do with segments is you would turn this program into 3 segments. You would go over here and turn this program here into 3 segments. So let's see. I would give this program, now I would need a third pair of base and bounds register. So I'm not going to draw that in the picture, but imagine I put a third segment here. Okay. Okay. So one of these segments will be one segment will be code, one segment will be heap, and one segment will be stack. Okay. And the heap will be just that size there. I won't have any of this space in between. Okay, so I'll have the heap be exactly what it starts out at. That's what the heap starts out at. And this is what the code starts out at. And this will be the stack's starting size here. Now I'll change the stack so that it grows downward. See, here they have the stack growing upward. So go over here and think of this as the stack. So we'll make this one the stack. Okay. And the stack we'll have to think, oh, and this is going to be the heap. Oops. And this segment here is going to be the code. Okay. So we have 3 segments, code, heap, and stack. And we need to make it so that the stack, we have to think of the stack as growing, make the stack grow downward. Okay. Okay. Just like, and same way, see, just like the heap grows downward, because memory, we can't change the base register when we want to grow. We're going to want to, when the stack grows, we're going to grow, remember, by changing the bound register. You can grow a segment by changing the bound register, but that means you can only grow downward. So the heap can grow downward, the stack can grow downward. Okay. All right. So now we allocate to this program 3 segments, a code segment that's just the right size, a heap segment that is the size it initially starts out at, and a stack segment that is initially how big you think it needs to be. Then at runtime, if the heap needs to grow, the heap would ask the operating system to increase the bound register of that segment. As long as there's a little bit of room here, you can increase the bound register of that segment. Okay, same if the stack needs to grow, you could ask for the bound register of the stack segment to be bumped and you can grow the stack. Okay, so you can grow these guys and then you don't have this wasted space here. Instead of wasting space on the assumption that, or on the guess that it might be needed, you allocate these things to be exactly what they are. You give them each an initial allocation that you think is reasonable, but then they can grow. Now, there is a bit of a problem. What if this guy wants to grow too much? Okay, if he wants to grow more than that space there, then you can still grow him, but you'd have to do a very elaborate process of defragmentating memory. See, remember we talked about one of the big problems. The big problem is external fragmentation. External fragmentation, let me see if I can. External fragmentation are these chunks that are empty, like this is external fragmentation, this is external fragment. See, it's the space between here. These are the external fragmentation. They're outside of the processes. This was internal fragmentation. It was a wasted space inside the process. If I want to grow the heap more than that gap there, I might be able to do it, but I have to do a lot of rearranging of memory. I have to defragmentate. In this case, when we use the word defragmentate, we mean defragmentate the external fragmentation. I'd have to, for example, uh, shift this guy up and shift this guy down. Okay, so if I, for example, shifted this guy up by changing his base register up to here and changing his bound register appropriately, and then copying all the code, and I shifted this one down, I could put a bigger gap between these two. But defragmentating in this case requires you to copy segments from one part of memory to another, which is really time consuming. So that's the big problem, is you still have external fragmentation, and defragmentation is very, very time consuming. Okay, it does not solve external fragmentation, and defragmentation is just way too time consuming. It's doable, and they did do it back in those days. Okay, they did do it, but it's the big failing. It's the problem that motivated them to find a better solution. Because this works well, as we'll see as we talk about these other things. It solves these other problems pretty well. We see it solves internal fragmentation pretty darn well. You know, you don't have to do this kind of a memory layout where you have to just pessimistically allocate a lot of space. You know, that's considered a pessimistic allocation. You allocate a lot more space, not having a clue whether you really need it or not. Okay. So with segments, you don't have to do this pessimistic allocation. You can just give a conservative allocation to start with. You know, you give conservative allocations to start with, and then if you need to, you can grow. But growing might require defragmentating. Normally what you do is you try to space these segments out in memory so there's gaps between them, but that may not work for very long. If this thing, you know, after things grow and or processes die and new processes are created, you end up with highly fragmented memory, and you may just have to at some point defragmentate memory by doing all this copying. Okay, so that's how you think of solving the the internal fragmentation problem. You can, by having multiple segments dedicated to specific jobs, like a code segment, a heap segment, and a data segment. Then you can allocate the heap and data segments optimistically to the size you think they need to be, but then they can grow. And remember, you grow them by just changing their bound register. If you don't need to move them, you grow them by just changing the bound register. If you need, if there isn't room for changing the bound register, then you have to defragment memory. Okay. Okay. Now let's see. What's the next thing we should talk about? The next one is, how can processes share memory, and why would they want to do that? Okay. Now let's go back to this other handout. They had kind of a nice picture of that. Okay. In this folder, there's this handout here from another class that has a nice example of what we would mean by sharing segments. So it's the second to last page in here. Okay. Here's two processes, each with two segments. Okay, so this is process one, and there's what his segment table looks like. Here's process two, here's what his segment table looks like. Now, we imagine one of these is running on the CPU, and one of these is well, actually, you could imagine this is running on CPU 1, and this is running on CPU 2. Each CPU has its own memory management. Actually, I never mentioned that, but in this picture, if you have multiple CPUs, each CPU has to have its own memory management unit. Okay, so you could, if you have two CPUs, you could have this CPU, this process running on one CPU, and this process running on another CPU. If you have only one CPU, this process would be would be running on the CPU. This might be in the ready state, which means that this table is in its process control block. Okay. Now, if you look at the page table, you see that that base register is the same as that base register. So the base register of this segment and the base register of this segment point to the same place in physical memory. And what's there is the editor code. So this, what they're imagining is that there's two instances of, say, Notepad. This is actually a really good example. This is Notepad editing 1, file, and this is Notepad editing another file. Okay, why would you need 2 copies of the Notepad program in memory? The code is read-only. Programs only read their code. So you could have the code in memory one time, okay? Then this CPU is stepping through the code itself. One CPU is stepping through this code to edit this. Then this segment is the data, the file that's actually being edited. So there's the code of the editor. There's the file, the data that would be in the file that it's editing. Here's another instance of the editor. This is essentially the same code. The code is just in physical memory one time, but this CPU, whatever this editor is doing, this editor doesn't have to be doing the same thing. They're 2 independent instances of the same program, like Notepad, but because this one's got its own CPU, it's stepping through this code one way, while this CPU is stepping through the code a different way. Okay, so these processes now share their code. So that means you've saved a lot of physical memory. Suppose you had lots of people editing files on a computer. Back in the old days, this was really common, actually. This was an important use case. You might have a mainframe computer that was used by a company, and there could be hundreds of people editing data on the computer, and they would only really need one instance of the editor program in memory for maybe 100 people to be editing files. Okay? Now that would be a lot less. That was back in the days when memory was tremendously expensive. So not having to have 100 copies of the editor in memory was a huge savings to them. Okay, now that's not what modern Windows does. Okay, like in modern Windows, if I go here and I start up 2 copies of Notepad. Okay, so remember, Notepad is sitting in the Windows directory inside the Windows System 32 directory, under the System 32 directory. Okay, there's Notepad. Okay, so I can start now. I can call up Task Manager, go over here to Details. Okay, and if I start up one Notepad, there's my there's my Notepad process that I just started. Okay, and if I start another Notepad, there's my other Notepad process. Now, you might think that they're doing the same thing that this was, I'm sorry, where's that picture? Did I close it? Oh, it was up here. I'm sorry, I forgot where it was. Okay, you might wonder if Task Manager is doing this. There's 2 instances of Notepad. So is it got the code for Notepad in memory once, and then the 2 different data in memory 2 different places? And the answer is no. Windows actually loads Notepad into memory twice. So it does not do this trick. But Windows does do code sharing, but it does code sharing in a different way than what's done here. This is the old-fashioned way of code sharing. What Windows does now is a slightly different kind of code sharing. Okay, so now here's what Windows does. When you write a program, there's a program is made up of code. Okay, how much code is in a program? There's code you wrote. There's code that the C programming language wrote. Okay, there's code you wrote. There's code that the C programming library code. A good example of that is printf. You didn't write printf. The C programming language wrote it. And then there's code that Windows OS, the Windows operating system, wrote. A good example of that is create process. Okay, right? So your program's essentially got 3 pieces to it: your code, the C code, and the Windows code. So every function, either you wrote it, the C language wrote it, or the Windows operating system wrote it. Okay. Almost every process running on this computer is using, most of them were written in the C language. A large chunk of these were written in the C language. So a lot of them call printf and fopen and scanf, all these C library functions. The modern idea is that somehow if every one of these processes had its own copy of printf in memory, you'd be wasting a lot of space in memory on printf. Okay, do you really want to copy a printf in memory 1,000 times? Okay, so what modern computers do is they create what we would call a segment that holds the C, all the C functions. All the C functions are in their own segment. Okay, then that segment is in memory one time, and then that segment is shared by all the processes. So what we do is, in a modern system, we don't share the editor, we share the C library. Oops, we share the C library. Now let me show you where that actually is. Okay, if you go to the computer, open up the open up your C drive. The Windows operating system essentially ends in the Windows directory. And then the real bulk of the operating system is in this system32 directory. This is really where the operating system is, okay? And then notice that there's almost 5,000 files in this folder. But if you go to MSV, MSV stands for Microsoft Visual Studio. So you go, see these files here? There's a whole bunch of them. Look at the one we want. See this one here. It's called MSVCR. No, what was that? CT. No, see the little highlight underneath it? File description. Windows NT CRT DLL. CRT stands for C Runtime. This is the segment that holds printf, scanf, fopen. It holds all the C library functions. That's the segment. And you can actually open it and look inside of it. Now, on my machine, I have a program that this is not something that comes with Windows. But if I right-click on this, I can see what's called View Dependencies. It lets me open a DLL. Oh, DLL stands for a Dynamic Link Library. The idea is this is a library. It's the library of C functions. And the dynamic part's kind of hard to display, but the middle L, link, means it's going to be linked, which in our case is this picture over here. It's going to be linked into several different programs. Microsoft thinks of it as linked in. People also think of it as being shared. We're going to share that segment among multiple programs. In fact, Linux doesn't call these DLLs. They call these guys here shared objects because they become segments that are shared among all the processes that are running. Windows calls them dynamic link libraries. Linux calls them shared objects. Okay, I can look inside of this guy. Takes a little while to open them because the program analyzes it as it's opening it. So it's actually real slow to open. Dependency Walker is a program you can add to your computer. It's a really powerful debugging tool that maybe later on we'll talk a little bit more about it, but it's a really nice kind of debugging tool that you can add to your computer. Okay. So I've opened this DLL in this program called Dependency Walker. Here is a list of all the functions that's inside of this DLL. Okay. Now, for example, if I go down, if I put them in alphabetical order, and I go down here, there's all the printfs. Okay, there's the F printfs. Okay. There's the F printfs. Okay. There's F puts. There's free. See, you can start seeing that there's F scanf. Okay. Then if I go farther down, I'll get to actually the printf function. There's printf. Okay. See, this DLL, this file here is a segment. Okay. It's essentially a segment, and that segment can be shared in as many processes as we want by using this idea here of putting the segment in memory someplace with a base, then putting that base in everyone's segment table. You put that same base in everyone's segment table, then everyone is calling those functions in that one instance of the DLL. Okay, and then that DLL holds all of the C library functions. Okay. Now, the same is true for the Windows library functions. The Windows library functions are another DLL. Okay, and offhand, I don't know if I remember which one it is. Okay, so I'm going to close this one. Oh, and for some reason, Microsoft has 15 different versions of the C runtime. Like what? Let me hover over that. See, it's the Windows NT C runtime DLL. What's this guy? The Microsoft C runtime library. What's this guy? The Microsoft C runtime library. What's this guy? The Microsoft C runtime library. Why do they have 15 versions of this? No one knows why, and it's a real nuisance. It causes all kinds of problems because some programs want that version of the C runtime library, some programs want that version of the C runtime library, some programs want that version. And if you don't have all of these, and these are not all put there by Microsoft when you buy Windows, some of these are put there by Visual Studio. Every once in a while, you'll run a Windows program, and you'll get a pop-up error saying this program doesn't run because you don't have one of these DLLs because you don't have Visual Studio. And sometimes when people write their own code using Visual Studio, they don't pay attention to which one of these DLLs they're linking to, and then they make the program available on the internet, and then you have to go dig out from the internet somewhere how to get these DLLs. Many of these come with Windows, but not all of them. Some of them have to be installed separately. After you install Windows, you have to download these. Notice that there's what, something like 23 different versions of the C runtime library. Well, that's IOStream DLL. Okay, starting here, C runtime library up to, I think it's here. There are 20 C runtime libraries on my computer. There might be a different number of them on your computer. Why in the world would you have 20 copies of the same? You ever heard of the expression? If you're curious, Google this expression. This has been referred to for years as DLL hell. This idea that you'd have multiple, somewhat slightly different versions of DLLs on your computer, and it would cause all kinds of grief. It's been one of the biggest complaints about Windows for many, many, many years. It's not as bad as it used to be. Windows 10 does not do DLL hell as bad as it used to do. Okay, but it was just, I mean, it's got its own little Wikipedia page. Okay, yeah, it's a problem with Microsoft having multiple copies of DLLs on your computer that had slightly different names. Hackers love this stuff. If they want to hide a virus on your computer, guess what's a great name for a virus? MSCV something. Make it MSVCP140_7 or something like that. They would hide malware in files that have names very vaguely familiar, vaguely similar to DLLs that are supposed to be on your computer, and it just caused all kinds of grief. So I don't think Microsoft's ever quite explained why. Well, actually, they have. There's all kinds of bad technical reasons for them to have needed to have all these multiple DLLs on your computer. Okay, there are reasons for every one of these, but they're not great reasons. But there is a reason. Microsoft can tell you exactly why that file is there, and why that file needs to be there, and that file needs to be there. And they'll tell you why that file needs to be there, and that one needs to be there. Like they'll have a reason, but it's not going to be a good one. Okay. All right. So that's what modern computers do. They do they share. Now I'm going to call them shared segments. Yeah, they really aren't. We're going to be using modern computers using pages, but it's still the exact same idea here. You think of the DLL as one segment. You put the DLL in memory. You give it a base. And that could even be done when Windows boots up. You can just put that DLL in memory because it's going to be used by almost everybody. And then when programs are run, they get in their segment table, they get one segment that has the base of your DLL. And then everybody shares that DLL. That cuts down on memory usage by a massive amount. Because in Windows right now, you can see that there's by default hundreds of processes running on every Windows machine. Every one of those processes needs the C runtime library. Even programs not written in C have the C runtime library built in. Like Python programs will have the C runtime library in them because Python programs make use of C functions. And then there's also the same thing's true of the Windows runtime library. So that's another DLL that gets, actually I know where it is. If I, did I close Dependency Walker? Yeah. If I analyze one of these DLLs, we said before that every function ends up, like suppose you do printf. You call printf. But we said before that printf can't talk to the I/O devices. So printf actually has to make a system call to the operating system. Okay. So there's no way that printf can actually print anything. It has to call the operating system. So the DLL that holds printf. So I go down here. Here's printf. Okay, the code for printf is in here. I'll find it. Okay, there's the code for printf. Okay. Here's his address too. There's its offset in the segment. Okay, its entry point, that function's entry point, there's its offset in the segment. Okay, but that function has to make a system call. He has to call, printf has to eventually call the Windows operating system. So you see that this program is showing that this DLL is going to call that DLL. That's the operating system. It's called NTDLL because this version of Windows, its original version in 1993 was called Windows NT. So that name still shows up in here. It's called the NTDLL. Okay, so because the original version of Windows was Windows NT. Okay, and then down here are all the real hardcore, like create process should be down here. I don't know if we can find it because it may have it usually doesn't have the same name as it has in the Windows library. But somewhere in here would be create process. There's just a massive number of functions in here. Okay, all right. So the C runtime functions, they call NTDLL functions. So NTDLL, and then the NTDLL is going to be in this folder here. Is it there? I'm not sure I think it's in this folder. Oh, right there. I wasn't, yeah, there's the NTDLL. Okay. That's a fairly large DLL. Oops. Oh, and I lost it. Okay. Okay. Now if I hover over it, NT layer. Okay, that's the layer that holds the system calls between the user level and the kernel level. So that's the NT layer DLL. It provides the contact point. This is where you make your system calls into. You make your system calls into the NTDLL. Then the NTDLL calls into the real operating system. It's actually it's a library of system calls that call into the real operating system. So this is not actually the real operating system. This is the interface to the real operating system. So you make your calls into the NTDLL, and it makes the system calls into the heart of the operating system. And I don't remember offhand where the real heart of the operating system is. It's somewhere in here. Somewhere in here is some more DLLs that are the actual kernel itself. Oh, I wonder if you open NTDLL, I don't know if it shows you. Oh, it doesn't depend on anything. See, they just show it as a dead end. See, they don't show it calling anything because what it calls is the true operating system. So this DLL dead ends there. All other DLLs call, and any other DLL, the DLL functions would call functions in some other DLL. And then functions in that DLL will call functions in some other DLL, and then it dead ends here. This is where, because the next point, these guys, the things that are in here call the actual kernel itself, which is not something that's public. You cannot look inside of the kernel like you can look inside of this NTDLL. Okay? All right. So sharing physical memory is real important because of these. You can see, sharing DLLs, first of all, realize how unbelievably important this is to Windows. Remember, this is the System32 directory. Okay, this is, I said, like, this is where the operating system sits. There's, in this directory are 4,800 files. Now watch this. Group them by type. Okay. Now, what's in here? There's 600 programs. Okay. And 3,500 DLLs. So what is the operating system? It's 600 programs and 3,500 DLLs. DLLs and the idea of sharing segments is at the heart of the architecture of Windows. Almost everything in Windows is a DLL, like the networking code, the file system code, anything you can anything you can think of that Windows does, opening pictures, showing movies, all the little functions of the Windows operating system are buried in some DLL. Sometimes you can hover over these DLLs and find out what they do. Application Information Service, that's a pretty generic name. Authorization Framework. Okay, so there's going to be something that allows you to authorize, logging in. That's going to be something that has to do with the operating system's ability to log you in. Okay, so all kinds of, the operating system is built as thousands of DLL files, literally 3,500 DLL files. So once we learned about this, notice that once we learn about this idea of shared segments, we're actually starting to see how an operating system really works. This idea of sharing a segment between two processes now becomes, we see, a cornerstone of the whole Windows operating system. It's 3,500 DLLs. And one of those DLLs is the root of a tree, essentially, of DLLs. That guy, all the other DLLs essentially feed back into him. Every other DLL will feed back into him. He's the boundary between the DLLs and the actual operating system itself. Okay, the actual operating system itself, I'm not sure where it is. I don't know if I don't remember offhand if it's one of the DLLs is essentially the operating system, or if it's one of these programs. If one of these programs really isn't a program, but might be the actual OS itself. If you call up Task Manager and you look at who's logged in as what. See, right now I'm logged in as classroom. And then there's system here, okay? Either one of these, no, that's not the operating, those are not the operating system is probably one of these. You see things with no name, no username? Somewhere in here is the thing that's probably the operating system. I'll bet it's somewhere, it's one of these things. It's not these SVC hosts. I don't remember which one it is. Somewhere in here is a process that essentially is the operating system. Okay, and the NTDLL is everybody's entryway into the operating system. You do the system calls. System calls go through NTDLL. Okay, all right. Now let's keep on going through. If you can share segments, we just seen that you can share code with them, but you can also share data. If two programs, instead of sharing code, shared their data, which is actually a fairly common thing to do, instead of sharing code like we talked about, you could take a piece of data, a data segment, and put it into two processes, segment tables. In that case, what happens is, suppose this data is, let's see, let's go back over to, okay, just flip this picture around. Imagine that's program 1, program 2, and that's the shared data. Okay, so just kind of flip it around. Imagine you had one program and another program sharing this data. What you could do then is anytime this program wrote something into that area, this program could read it. And anything that this program wrote into that area, this program could read it. So they have a shared, it's like a Google Doc. Think of this would be like a Google Doc. These, anything he writes into it, this one can read, and anything he writes into the other one can read. The two processes can talk to each other that way. So if two processes need to communicate, in our case, that would be, this, for example, this is how all the Chromes are going to communicate. All these Chromes share some data segment. There is a data segment in memory. If you dug deep enough, you could probably find it. Later on, maybe we'll learn how to dig deep into these processes and look at their segment tables and their memory tables. But these Chromes, they're going to all be sharing some piece of memory so they can talk to each other. So that you can run Chrome as if it was one program. Okay, but when it's actually multiple processes, notice how they're sharing this framework here. Okay, so they have to be somehow communicating with each other to be able to share the fact that they're in this framework together. So all these Chrome processes will have some data segment that is core to, that's shared by all of them, that they can communicate through. Okay, and that's called inter-process communication. And that's another, if you just Google IPC, it's not quite at the top, but the third link is inter-process communication. Okay, so IPC pretty much, it's real commonly refers to this idea of how can processes talk to each other. There are many forms of inter-process communication. The one we're talking about is shared memory. This one here. They call it, it's not called shared memory, but it's usually referred to as memory mapped file. Okay, it's essentially this thing here. Memory mapped file is the fancy term for having two processes share a segment. Okay, there's a good reason to call it memory mapped file, but it really boils down to sharing a segment. Two processes that would have a segment in both of their segment tables, and they can both refer to that segment. Okay, so you could share code or you could share data. Okay, once you can share segments, you can share code, which is ubiquitous, and you can share data, which is common. Sharing data is not as common as sharing code because there are other ways of doing inter-process communication. You don't have to do it by shared segments, okay? But sharing code is always done by shared segments, okay? Now, let's look at it. Okay, so that's one big thing that segments can do for you. When you have a segment table and you have multiple segments, you can have two processes share segments, okay? Now let's look at this kind of funny one. How can a program be bigger than physical memory, okay? Okay, now the way you might do that is, here's an example of a program that's got 1, 2, 3, 4, 5 segments, okay? So this program has 5 segments. If not, to do this trick of having processes have more virtual memory than physical memory, you have to have the feature that segments can be on the hard drive. So you have to extend this picture to being that there is a hard drive, and a segment, instead of being in physical memory, a segment could be in the hard drive. Okay, that's referred to as being swapped out. Okay, so now, so suppose this program had 1, 2, 3, 4, 5 segments, and the segments were really quite big. Now, no one segment, every segment has to be big enough to fit into physical memory. But suppose you had 5 segments that are all almost as big as physical memory. Okay, so you could have a bunch of segments off on the hard drive. Okay, then what would happen was when you access the segment that was on the hard drive, the operating system would copy it into memory. And if there wasn't enough memory to copy it in, it would take a segment that's in memory and copy it to the hard drive. Okay, so the operating system would swap out a segment, that's copy a segment to the hard drive, and swap in a segment, copy a segment into memory, and then it would adjust the, yeah, those segments could, for example, share a base. You know, they might even be using the same base. Okay, and you might do that by having them have the same base. So if two segments have the same base, if you switch from one to the other, you know, what you could do is you could have the same base appear twice in this table. Okay, you could have the same base appear twice in this table. So then if you access segment 1 at that base, you would check that that base is in memory, and if it is, you'd use it. If that base is not memory, you'd swap out the segment that's sitting there at that base and swap in the one that you want. Okay, so that if people wanted to write the operating system to allow swapping of segments, now you have to have this. It involves putting a lot more code in the operating system, but you could potentially have segments that are large. A program could have multiple large segments, but they can't all be in physical memory at the same time. Some of the segments will be sitting on the hard drive. So then when you jump from that segment to that segment, it might actually take a while because it may be that that segment has to, that this segment has to be copied out of memory, this segment has to be copied into memory. Then you can start working on this segment's data. Then if you, for example, went back to that segment, the operating system might have to copy this segment to the hard drive, copy this segment back into memory. Okay, we're going to see page tables do the similar kind of thing. So it's actually all modern operating systems do this, but here you would do it by copying this whole segment out to memory, copy this whole segment into memory. So segments will be copied to the hard drive, then other segments will be copied from the hard drive back into memory. And then you have to have a special place in memory to store the segments. Okay, if you go back to this computer, go back to the hard drive on this computer. If I right click here and say view, let's see, no, actually I want to go up here, sorry. If I go here to view options, change folder and search options, I go here to view and I say hide protected operating system files. I want the operating system to show me some hidden files. It warns me I shouldn't do this, but it's okay. Then I click OK. What happened? I should, well, let's see. I didn't see what I want to see. Let me try again. So here's another one, show hidden files and folders. Okay, that showed a lot more. See this guy? That's where segments get copied to when they get copied to the hard drive. We say that a segment would be swapped out to the hard drive. And there's a special file on the hard drive to hold segments when they're swapped out. So that's the swap file. Okay. Okay. So Windows has, it's usually on your C drive. There's a hidden file called the swap file. Okay. And that's actually what it's there for. It's for this idea here that if you wanted to have programs that were larger than virtual memory, if you want to have programs that are larger than virtual memory, you can make them, you can cut a program up into lots of segments that the size of the segments add up to more than virtual memory, but some of those segments have to be stored on the swap file. Okay. So some of the segments would be sitting in the swap file. When your program starts up, your program would start up. All these segments are part of your program. The operating system would move some of the segments into physical memory and some of the segments into the swap space. Usually it would be the compiler to decide which segments load into memory and which segments load into the swap space. Okay, so your program would start up. Some segments would be in memory, some segments would be in the swap space. If you tried to access a segment that was in the swap space, then the operating system takes over. It has to copy some segment out of physical memory into the swap space, copy some segment from the segment you're accessing, copying it from the swap space into physical memory. Okay, so the operating system would have to do a lot of this work for you. Okay, so segments allow for this kind of thing to happen, but that requires the operating system to do this trick of having a process larger than physical memory. You can do it, but it requires it's not just you don't do it with just segments. You do it with segments and a bunch of extra operating system code that would then that would have the notion of the swap space, and it would have the notion of if you access a segment that's not in physical memory, but it's in the swap space, the operating system knows how to handle that. Okay. All right. So almost done. Okay. So okay. So we've outlined the idea of using multiple segments, and we've seen that they let us do all these kind of neat things. Almost eliminate internal fragmentation, can optimize memory by sharing lots of code that would normally be repeated code all over memory. We can share it. We can actually let processes talk to each other if they want to. We could process large data sets if the operating system lets us, by having segments that add up to more than the actual size of virtual memory. Actually, the segments could even add up to more than physical memory. The sum total of your segments can be more than that would fit into physical memory. Okay. Any one segment has to be smaller than physical memory, but the sum total of all the segments could be more than physical memory. Okay. Now, on Wednesday, we're going to start talking about page tables. Page tables are a more complicated way to solve all these problems. And page tables will also solve the external fragmentation problem. The external fragmentation problem is this chunk of memory here, this chunk of memory here, and this chunk of memory here. That's the external fragmentation. If you want to load a segment that doesn't fit here, here, or here, you have to move everybody, defragmentate memory, get all your free space in one chunk, and then you can load somebody big. Defragmentation is when you get all the free space in one chunk. Segments don't help with that at all. They do nothing for solving external fragmentation. Okay. Okay. Let's see. So we've run out of time. So if you have questions, I'll put these little. I'll put the video from the recording of this video up, and I'll put these notes. And we drew this one picture. Forget where it is. Oh, I'm sorry. Yeah, I'll put this picture that we drew. So I'll put everything that we did up on the website. Anybody have any last minute question? Okay. All right. So I will, let's see, stop sharing. Okay, I'll go ahead and end the meeting right now. All right, bye.